So those fans will have, let's talk about centrifugal fans. So for induced draft they could use forward or radial, and for forced draft they will use backward fans. So because the pressure on those fans is not really that much, you can assume constant specific volumes through them as if they are incompressible. So we'll treat them as if they are pump, not really as a compressor, because the delta P is not that big. And so if we want to calculate the work, it will be just like a pump. How did we calculate the specific work of a pump? It's what? It was H delta H, right? H minus H, and we approximated the H as specific volume multiplied by delta P. Remember that part when we said U and the internal energy does not change that much? So the delta H become almost specific heat multiplied by delta P. So that would be the specific work. So the power per m dot is specific volume multiplied by delta P. Okay, and of course there is you will have an efficiency attached to it to make it, this is the ideal work, and so you divide over eta to make it a little bit bigger. And if you want to turn from watt to horsepower, you divide over 745, because they usually specify them by horsepower. Okay, and we'll let the control of those things we'll talk about this in another course, experimental fluid. Okay, but there is like smart way to control it by controlling the speed, and there is a dumb way to do it by using damper control, which add delta P on them. Then you will end up basically kind of like shutting or throttling them so that they can give you less and less flow rate. Okay, heat exchanger. All those feed water heater are basically shell and tube heat exchanger, except for the open feed water heater, which is basically just one big mixing chamber. And you can see for the high pressure ones, they look like a tank. Look at how heavy the pipe, the wall is, because they operate at very high pressure. So the feed water heater number 6 and 7, the last two before the pump, they are operating at the pump pressure. Sorry, they are operating at the boiler pressure. So 6 and 7, the last two feed water heater after the boiler feed pump, they are running at the boiler feed pump pressure, or basically the boiler pump pressure, right? So that's why they are usually very heavy steel used on them. The other one could be a little bit easy to build because they don't have that high pressure, and they would be you can go 2 pass, for example. You can go like this and go back again, and so some of them are vertical, some of them are horizontal. And the heat transfer equation and the thermodynamic equation are used to solve those heat exchanger. So you would say that energy in equal energy out, right? Whatever the water would lose, whatever the water will gain will be equal to whatever the steam would lose, right? So this is how you can calculate the delta T across it for the water. And in order to come up with the area, we use the heat transfer equation. Q is UA delta T, and we went through this when we were discussing the ocean thermal power plant, right? The ocean thermal energy conversion, and we said how we can use the logarithmic mean temperature difference to be able to calculate a fair temperature difference. So for counter and parallel flow and counter flow, we just use that formula. But for all the other weird configuration, shell and tube with a 1 shell pass or 2 shell pass or cross flow, we use a correction factor, and that correction factor comes from those charts that we had them in the in the heat transfer book, right? Very good. So now the open feed water heater, is one big tank, right? Where the steam get flushed with the water and they all mix, and we do this. Every power plant has to have one of those open feed water heater. Why? So that they can liberate any undissolved, basically any dissolved gases in them. Any O2 or N2 that leaked into the condenser, because he's really running under vacuum, you can liberate them and eject them in that place. Okay. So here's another sketch of this open feed water heater. So I'm showing the water level over here and how he's bringing the steam, and he's basically trying to liberate, and this will be slightly above the atmosphere so that when you open the air vent, the undissolved gases basically just rush out. Okay. Here's how he's showing you how he's doing this, how he's making the steam hit the water so that they can basically try to liberate the any O2 and N2 that is basically dissolved in the water. Here is a sketch of the steam power plant. This is in Jenks power plant, and you can see the size, how big they are. Okay, the low pressure turbine, the one that they basically send it in both direction, that's how it looked like. And you can see how large those plates are, and you can imagine now how larger they will get if they have done this in one pass. They would be super large that it would be ridiculous. The centrifugal force will just snap them out because of the speed they are running at. So that's why they break them into two, setting them back to back. Okay, and this is the first stage of the high pressure turbine, and you can see how is it. We'll leave this for experimental fluid, but this is basically called an impulse turbine, where the high pressure steam just come and change direction without really losing pressure in this part. So all the pressure drop is happening in the stator, and the rotor is just for changing direction. Okay, I'm gonna skip this part. We'll leave this for experimental fluid course. Okay, we'll leave this part. All those velocity triangle, don't worry about them for the steam power plant. Okay, and this is when he talk about the condenser, right? So this, let's remember that the Rankine cycle is basically a way for us to turn QA into work, and the rest is gonna be Q rejected, right? All those feed water heater and all those turbine, at the end of the day, this what happened. You are generating fuel, you are generating heat in the boiler, turning some into work net, because there is turbine and there is pump, and the rest is Q rejected. So if I ask you for Q rejected, you can just basically say, I did this 1 year and a lot of students didn't get it. So Q rejected is simply just Q add minus work net, right? And the eta thermal is simply work net divided by Q added. Okay? So when we say a 40% power plant, what that mean? It means that 40% of the Q added is gonna be work net. And where is the 60% go? It go to Q rejected, right? So 1000 megawatt power plant with wet cooling tower. He has big cooling tower that cool the condenser, and the thermal efficiency is 45%, and the delta T cooling water is 14K, and the CP of cooling water is this 4 kilojoule per kilogram. What is that? He's saying that this condenser or this Q rejected, he's gonna remove that heat by sending the steam into a condenser, right? And the condenser bring cold water, and that cold water will get a little bit hot while turning the steam into saturated water. So that is the delta T cooling water. Okay, this is how much he's allowed to heat the cooling water of the condenser. Why there is a maximum limit on how much the cooling water will get? Because maybe that cooling water is going back to the river, coming from the river into the river. In this example, he's saying no, he's sending it into one big cooling tower. Okay, so that is fine, but the point is sometimes there is a limitation on the cooling water because you don't wanna boil the fish in the river. There is environmental regulation for how hot the cold water go back to the river, for example. So he can only heat it up 14 K. Alright? So first of all, he won't Q rejected. How much Q rejected? How do we do this? That is the work net, right? And you have the efficiency. So you can calculate how much is Q added, and you do subtraction, you get yourself Q dot rejected. And he's asking about how much cooling water do we need. Well, that can be done from this, right? So in this condenser, the Q rejected is simply m dot cooling water multiplied by CB cooling water multiplied by delta T cooling water. Correct? So if we can calculate this Q rejected, I can calculate this if I know this, guys. And I do. Those were given to me. Make sense? Okay. What's important, I think, and some people don't miss, is that they get lost in with those big power plant, and they don't realize that it's simply Q added is divided into two parts: work net and Q rejected. That's what's happening over here. Okay, so you can see Q rejected, Q add minus work net. He calculate Q rejected from that, and then first law of thermodynamics, he calculate m dot cooling water. Now to size a condenser, you need to tell yourself how much heat I need to get out in that condenser depending on its size, and they will tell you what is the steam flow rate that's allowed to go through there, the surface area, and you can figure out how much how many tubes are needed, and what is their dimension. Okay, so there are tables to pick the condenser size from. So now over here, that cooling, that condenser, once we decided that's going to be this much, this size with this many tube, he need the cold water to come in and then the hot water to leave. This could happen from the river, right? The one that when I was undergrad, I was trained in a steam power plant sitting next to the river, and that's what we did. We just took water from the river and send it back to the river. Okay, so the problem with this is that of course you have screen here to stop the fish from coming into your condenser, but you get a lot of mud, and therefore that condenser get dirty, and that condenser need to be cleaned, and that condenser you need to clean they send like those rubber ball that goes through, and they are small ones so that you get most of the mud, then you send bigger one to clean a little bit more, and then you send even bigger one that kind of like scratch the tube clean. But if you don't have a river nearby, or you don't want to handle the dirty water, then you can have your own cooling tower. So that cooling tower take the hot water, spray it in the air, and then the air will cool it, and then you get the cold water back into the condenser. So when you do this, you will be able to cool. Of course, that is a lot of money because you have to build a cooling tower, and that usually they are really big. You know, especially in nuclear power plant, those are huge structures. Why huge structure? Because they want the natural convection to help them, right? And they want the area too. So it's a huge exhaust. And if it's you'll be able to cool that water all the way down to the wet bulb temperature of the air, right? If this cooling tower is dry cooling tower, then you will cool the air. What's dry cooling tower? You don't spray the water in the air. So you don't lose any water. That's nice, you don't lose any water. But what's bad is you will not be able to cool the water more than or less than the dry bulb temperature. Okay, so in order to cool the water to the wet bulb temperature, which is always lower than the dry bulb temperature, you have to spray in the air, so the water would evaporate, and you'll be able to take it down to the wet bulb temperature. Okay, so now the cooling tower, whether it's gonna be really huge or whether it's gonna be short, that will determine whether you need fan to help or you can just do it all by natural convection. Okay, so short ones will have fans associated with them. Alright, this is the part when we say it's a wet bulb. So here, sorry, this is the dry cooling tower, dry cooling tower, but this condenser is wet condenser, direct contact condenser. We talked about this in the geothermal, right? We have seen this guy. So let me now show you the one that we had in Jenks. So those are the power plant that we have in Jenks, the power plant we have in Jenks, and this is a picture of the cooling tower. And because they are short, you bet there are fans sitting over here, or actually on the exhaust. There are fans that's pulling the air into the cooling tower. Okay, and those are just filters. Okay, so dry cooling tower, wet cooling tower. So the height is not for cooling or for wet or dry. The height is for, you want natural convection or do you want forced convection by fans. But the dry or the wet is because are you sending water in pipes without ever contacting the air, or you're gonna spray the water? And when you spray the water, you also spray it on some kind of backing material, tower fill matrix. In the old time, this used to be wood, and that wood will get rotten. And in order to prevent the wood from getting rotten, you will have to add some bad chemicals to protect the wood. But then that bad chemical will leak in the ground, and it will give you problems, right? So, but now they switch to basically plastics that will not deteriorate that much, and will still give you the surface area. So the whole idea behind this packing material is we want the water to stay forever in contact with the air. So you give them all those tray to trickle in, and you give them all those feature surface area to basically have more surface area with the air. So short one fans, long one natural convection, right? Air come in and leave in the exhaust. Here is the big ones, right? You always see nuclear power plant, you see those big cooling tower, and people would think, that is the nuclear power plant. No, this is just the condenser. Sorry, the cooling tower of the condenser, right? The power plant itself, nuclear reactor, is basically over there. So remember North Korea a few years ago in the Bush administration, when they wanted to show good sign they are dismantling their nuclear power plant, they show like basically the cooling tower being exploded, but that doesn't mean they shut down the power plant. That means that they switched from the cooling tower to say underground heat exchanger or something, or just like using water from the river, right? And here is a picture of the packing material that they spray the water on. Different configuration, and the whole idea is we want the water to have a lot of interface so that they have chance to evaporate, so that they have chance to cool. Okay. Again, condenser with a cooling tower, and that water coming from the river is just for makeup, right? But he's not supposed to lose that much, but he would lose. If you make it wet cooling tower, you will lose water, right? You will lose water, and that's why you have to compensate. But if it was dry cooling tower, you don't lose any water. So here he's showing you how much For a typical power plant, 1000 megawatt, that's like the one in Jenks, it's like 900 megawatt, right? So close to 1000. They will show you that if the tower has this much gallon per minute, how much one would expect to evaporate, and how much drift. Drift is basically what will just go because it's super tiny droplets, right? And here is fossil fuel power plant and nuclear power plant, and how much you should expect that you would lose, that you need to make up.